So we're given a circle where we know the area is changing at a rate of negative 1 feet squared per second. So the circle is getting smaller at 1 feet squared per second. However, what we are asked to find is the rate at which the radius is changing when r is equal to 1.5 feet. So we know that the area of a circle is pi r squared. So what we're going to do is we're going to take the derivative of the area so that we get pi times d2r dr over dt. So that we know the rate that the area is decreasing is negative 1, so we plug it in for dA over dt, and we plug in our other values, 1.5 as r, and dr over dt is not yet known. That's what we're trying to find. So then we plug that all into the equation, and what we end up getting is negative 1 over 3 pi times dr over dt, and then that equals negative 1 over 3 pi is equal to dr over dt. What we know from this is that the radius is decreasing at a rate of 1 over 3 pi feet per second when the radius is equal to 1.5 feet. For part B, we're asked to find the rate at which the circumference is changing when r is equal to 1.5 feet. So, we know that dA over dt is equal to negative 1 feet squared per second because of problem 1. So we know that C in any circle, the circumference, is equal to 2 pi r. dc over dt, the derivative of C is equal to 2 pi times dr over dt. So we already know dr over dt from part A because that was our answer. So what we do is we plug it in for dr over dt. So then we get dc over dt is equal to 2 pi over negative 1 over 3 pi. dc over dt is then equal to negative 2 over 3 feet per second because what we do is we get negative 2 pi over 3 pi and then we simplify it to negative 2 over 3. So because of this, we know that the circumference is decreasing at a rate of 2 over 3 feet per second when r is equal to 1.5 feet because the value is negative. So for this problem, we're asked to find the length of a man's shadow who happens to be 5 feet when he's 10.5 feet away from a 24-foot light. So we draw out this triangle and we end up using y as the distance from his shadow length. That's his shadow length. And x represents the distance from the pole. From this information, we're able to determine that there are two similar triangles. One of them relies off the height of the man, and one of them relies off the height of the lamp. So what we do is we set an equation that makes sure that they're similar triangles. So we have 24 over 10.5 plus y is equal to 5 over y. This instance, we cross multiplied. So we got 24y is equal to 52.5 plus 5y. Next, what we did was solve for y by itself. We got 19y is equal to 52.5. We divided by 19 to get y is equal to 2.73 feet. From this, we know that the length of his shadow is 2.763 feet when the man is 10.5 feet away from the lamp.
For part B, we are asked to find the rate at which the length of the shadow is changing when the man is 10.5 feet away from the lamp. X is the distance away from the lamp the man is at, and y is the length of the shadow, and x plus y is the overall distance. The height is 24 feet of the lamp, and the man is 5 feet tall. We are given that the rate at which the man is walking away from the lamp is 4.5 feet per second. We can use the idea of similar triangles to set up a proportion in order to solve for the derivative of y, which is dy over dt. Then we simplify the equation and find the derivative of y and x, and then we plug in 4.5 feet per second for dx over dt and solve for dy over dt, which is 1.184 feet per second. This means that the length of the shadow is increasing at a rate of 1.184 feet per second when the man is 10.5 feet from the base of the light.
For part C, we're asked to find the rate of change at which the tip of the shadow is changing at. For this, we had to take into account the distance the man is away from the lamp and the derivative of that, and the rate at which the length of his shadow is changing. For this, we find the values of the derivatives when x is equal to 10.5 feet. The derivative of the man's position from the lamp is equal to 4.5 feet per second. In other words, he's moving away from the lamp at 4.5 feet per second. dy over dt represents the length of the man's shadow and how it is changing. It is changing at a rate of 1.184 feet per second. So we add these two together to get our total change of the shadow, which is 5.684 feet per second. So from this, we can conclude that the tip of the shadow is increasing at a rate of 5.64 feet per second when x is equal to 10.5 feet. Or in other words, it's increasing at a rate of 5.684 feet per second when the man is 10.5 feet away from the light.
For part D, we're asked to find the rate at which the man has to lift his head in order to see the tip of the shadow. That is represented by d theta over dt. In the picture here, I have now added a theta, and we're trying to find when that value when the man is 10.5 feet away from the lamp and the length of the shadow is 2.763 feet, which is a result of part A. We are again given that the rate at which the man is walking away from the lamp is 4.5 feet per second, and we use the value from part B, which is 1.184 feet per second, to represent the rate at which the length of the shadow is changing. Then we set up an equation. We use tangent of theta equals 5y, because we're trying to find this part, this small triangle, and then we find the derivative of tangent of theta, which is secant squared of theta. For secant squared of theta, we can just use the triangle here, since 1 over cosine squared of theta is secant squared of theta, and cosine is adjacent over hypotenuse, so 1 over cosine squared of theta would be hypotenuse over adjacent squared. So you just solve for c here and plug that in for the top value, and then this part here would be the bottom value, and you squared that, and then you plug in dy over dt and solve for that, and then d theta over dt is 0.181 radians per minute. So the rate at which the man has to lift his head is 0.181 radians per minute in order for him to see the tip of the shadow when he is 10.5 feet away from the lamp. We had the conical tank problems. For part A, we are asked to find the rate at which the depth of the water is changing when the depth, or h, is 1 meter. So first, we need to draw the cone, and there are two similar cones, the one that is represented by the water and then the overall tank. We are given that the rate at which the volume of the water is changing is 78.6 meters cubed per minute. We can then use the volume formula of a cone, which is 1/3 pi r squared times height, and find the derivative of that in order to find the rate at which the depth of the water is changing. Since we're trying to get it in terms of h, or the depth, we have to solve for r, which is the radius, and plug that in for the radius in the volume equation. Then we find the derivative of the volume and plug in 1, because that's the depth at which we're trying to find the rate at which the depth of the water is changing, and then we solve for dh over dt, which is 38.121 meters per minute. This means that the depth of the water is increasing at a rate of 38.121 meters per minute when the depth of the water is 1 meter. For part B, we are asked to find the rate at which the radius of the water is changing when the depth of the water, or h, is 1 meter. So we are using the same drawing of the cone and the same idea of similar cones. We are given that the rate at which the volume of the water is changing is 78.6 meters cubed per minute. We still use the volume formula of a cone, which is 1/3 pi r squared times height, but this time, instead of solving for r, we're solving for h. and then we're plugging that in for the h value so that we only have the radius in the equation, which is what we're asked to find. Then we simplify and find the derivative of both the volume and the volume equation itself, and then we plug in 6.4 over 7.9 for r, since we know that the depth of the water is 1, and we can plug it into the similar cones equation, and then we solve for dr over dt, which is 30.883 meters per minute, which means that the radius of the water is increasing at a rate of 30.883 meters per minute when the depth of the water is 1 meter. For part C, we're asked to find the rate at which the surface area of the water is changing when the height or the depth of the water is 1 meter. The surface area is the same thing as the area of the circle here, and we are still given that the rate at which the volume is changing is 7.86 meters cubed per minute, and we know from part B that the rate at which the radius of the water is changing is 30.883 meters per minute. This time, instead of using the volume of a cone equation, we're using the circle equation to find the area, and then we take the derivative of that equation, and we're still using the same value for r, which is 6.4 over 7.9, and multiplying it times the derivative of dr over dt, and we get that the rate at which the area is changing is 157.2 meters squared per minute. In conclusion, the surface area of the exposed water is increasing at a rate of 157.2 meters squared per minute when the depth, or h, of the water is equal to 1 meter.